R2 is the set of ordered pairs x, y, such that x and y are real numbers. This is the visualization of R2. For example, if we have 3, 4, 1, 2, 3, 1, 2, 3, 4, and then this would be the point 3, 4. And I would like to say that different interpretations for this 3, 4. 3, 4 can be viewed as a point in the plane, and also it could be viewed as an arrow that goes from 0, 0 to 3, 4. That means it can be viewed as a vector. And when we view it as a vector, we can think of this vector as the vector that starts at 0, 0 and ends at 3, 4. Or we can think of this vector as a vector that starts at any other point. For example, if we want to draw this as a vector starting at 2, 0, then the vector would be something like this. Then this would be 3, 4. Let me just write that. 3, 4 view as a vector starting at 2, 0. Then there are different interpretations for every point in R2. They can be viewed as points or they can be viewed as vectors. When we think about vectors 3, 4, we have the length of this vector using the Pythagorean theorem. It would be, this is denoted by the norm of 3, 4, and this would be the square root of 3 squared plus 4 squared, which in this case is 5. For vectors, if we have a pair of vectors, we can define the inner product. And the inner product of two vectors, let's say if we have u1, u2, and then b1, b2, let's denote the inner product with a comma and two brackets like this. Sometimes it's denoted also like u1, u2, and we do that, b1, b2, and the definition is u1 times b1 plus u2 times b2. For example, 3, 4, that product with -1, 5 is -3 plus 4 times 5 is 20, is 17. Notice that we can also denote this as 3, 4 inner product with -1, 5. And this is just the same, 17. We have several properties for the inner product. And let's start with this one, property number 1. The norm of a vector, u1, u2 squared, is equal to the dot product of u1 of the vector with itself. We also have that the dot product is commutative. Let's suppose that u is u1, u2, and let's suppose that v is b1, b2. Then we have that u dot product with v is b dot product with u. Another property is that the dot product, if we call the vector c equal to c1, c2, then the dot product of u dot product with b plus c is the dot product of u with b plus the dot product of u with c. What else do we have? And we have that if lambda 1 and lambda 2 are real numbers, then it is like a generalization of this property. We have that u dot product with lambda 1 v plus lambda 2 z is equal to lambda 1 u dot product with v plus lambda 2 u dot product with z. These properties are very easy to check and they turn out to be very important. Let's give an interpretation for the dot product of two vectors. In order to do that, let me remind you the cosine law. The cosine law says that if you have a triangle and this angle is theta, and this is A, and this is B, and this is C, then this length square is equal to this length square plus this length square minus 2 times AB cosine of theta. That's the cosine law. And on the other hand, something that is very important is that if we have 2 points, let's suppose that we have the point u1, u2, and here we have the point b1, b2. If we want to think about the vector that starts here and ends here, this vector, if I call this u and this v, this is the vector v minus u. As an example, if we have that this is 1, 3, and here we have 5, 1, then this vector here is the vector 5, 1 minus 1, 3, which is the vector 4, negative 2. Notice that when you think about 4, negative 2 as a vector, if that vector starts here at the origin, it's just the same vector. But remember, this vector can be viewed as a vector that starts at any point. Then you do the difference of this with this, and this gives you the vector that starts at this point and ends at this point. Then let's suppose that we are going to think about a triangle. This is the vector u. This is the vector v. Notice that here we have another reason why this vector is the vector v minus u. When we do u plus this vector, it should give me this vector. That's the way we add vectors. We just connect the second vector to the tip of the first vector, and wherever that vector ends, that's the sum. Then we see that u plus this vector, which is v minus u, it just gives me v. That's the reason this vector is the vector v minus u. But let's forget about that now. And let's just think about this triangle. You have the triangle made by the vector u, vector v, and this. Let's call this angle theta. If we call this length A, and this length B, and this length C, then we have that A square is the norm of B square, which is B dot product with B. B square is the norm of U square, which is U dot product with U. And C square is the norm of B minus U square, which is B minus U dot product with B minus U. But using these properties of the dot product, we have that this is equal to B dot product with B minus B dot product with U minus U dot product with B plus u dot product with u. But remember that that product commutes, then this is just b dot product with b minus 2 times u dot product with b plus u dot product with u. And according to the cosine law, c squared is equal to a squared. This is because of the cosine law. Then this is just a squared, which is b dot product with b, plus v squared, which is u dot product with u, minus 2 times a, which is the norm of v, times v, which is the norm of u, times cosine of theta. And therefore, we get that these two things are the same, and we can cancel this with this, and this with this, and we can divide by -2, and then we get that u dot product with b is equal to norm of u, norm of b, times cosine of theta. This is a extremely important property. It tells us when two vectors are perpendicular, and we can compute the angle between two vectors just by doing something that is very easy, which is just the dot product of two vectors. Let's do some examples. If we have the vector 1, 2, 1, and the vector 3, 4, this is the vector 3, 4, and this is the vector 2, 1, and we want to compute this angle. This is u, and this is v. Then we have that we can use this formula, the dot product of u with b. It would be 3, 4, dot product with 2, 1, and this is 6 plus 4 equals 10. The norm of u squared is just u dot product with u, and this is 2, 1 dot product with 2, 1, and this is 4 plus 1, which is 5, and the dot product of b with b is 3, 4, dot product with 3, 4, and this is 9 plus 16, which is 25. Then, according to this formula, we have that 10 is equal to the square root of 5 times the square root of 25, which is 5, times cosine of theta. And that means that cosine of theta is just 2 over the square root of 5, and that means that theta is cosine inverse of 2 over the square root of 5, and we can use a calculator to compute that. We have cosine inverse of 2 divided by the square root of 5, and this is approximately equal to 26.57 degrees. This angle is 26.57 degrees. Something that is very easy to check, and it comes from this formula, is that when we think about the cosine function goes like this. This is 90 degrees, this is 270 degrees, this is 180 degrees, and this is negative 90 degrees. If we do the dot product of two vectors like these two, and we notice that that product is positive, that means that cosine of theta is going to be positive. And if cosine of theta is going to be positive, that means that that angle is between 0 and 90 degrees. If we do the dot product and we get 0, the only way that these two vectors, that cosine of theta is 0, is when the angle is 290 or 270. That means that the dot product of two vectors is 0 if and only if the two vectors are perpendicular. And also, if the dot product is negative, that means that the angle is bigger than 90. Then let me just finish by writing that down. We have that u dot product with b is 0, means that u is perpendicular to b. U dot product with b bigger than 0 means that theta is an acute angle. And u dot product with b is smaller than 0, it means that theta is an obtuse angle. It's an angle bigger than 90.